So today we're going to look at 3.2 series solutions near ordinary points. The method of using power series introduced in the previous section can be applied to linear equations of any order, but its important application is to second order linear homogeneous equations. So in this section, we're going to focus on second order homogeneous equations. This is a second order homogeneous equation, or equivalently, and first, we're going to define ordinary and singular points. We call x equals a an ordinary point as long as px and qx are both analytic at A. And analytic means that they px and qx equal to a power series. Otherwise, it is called a singular point. And we're going to look at a couple of examples. Notice in this example, px equals 1 over x and qx equals 1. X equals 0 is considered as a singular point. And the reason is px, which is 1 over x, is not analytic at 0. It's not defined at x equals 0. So x equals 0 is a singular point. Second example. Now in this example, let's check x equals 0 to see whether it's a singular point or an ordinary point. So we're going to look at px first, where px is sine x over x. And let's see if we can write it as a power series. So first, we can write out sine x in terms of its power series expansion. And then we can distribute 1 over x inside. So here, this right-hand side is well defined at x equals 0. That means px can be written as px is analytic at x equals 0. So x equals 0 is an ordinary point. Three. Now, let's check again to see whether x equals 0 is an ordinary point or singular point. Px, in this case, is already analytic. It's can be written as x squared. And the second term, qx, let's see if we can write it as a power series expansion. So in order to write it as power series about 0, what we do is we're going to do, so in general, if you have f of x, if you want to expand it about 0, then you're going to do f of 0, f prime 0, so you're going to calculate this right-hand side. So for our problem, we have 0 to the half, but when we take derivative, x is going to go to the denominator. This is our f prime of x. So then when we plug 0 in here, this is undefined. Therefore, this side is not defined at x equals 0. So x equals 0 is a singular point. Okay, so this is how to check whether it's a singular point or ordinary point. Now the use of it, the application of that is given by this theorem. So this theorem tells us if we can find an ordinary point of the given equation, then we can always find a solution of the form given by this power series. And the radius of convergence of this power series is at least as large as the distance from A to the nearest singular point. The singular point can be either real or complex. So now let's look at example. So let's first put it in the form with 1 being the coefficient of y double prime. To do that, we can divide both sides by x squared minus 4. And notice when x equals plus or minus 2, qx is not analytic. So these are singular points. So we know the series will have radius of a convergence of at least 2. And let's try plugging in y equal to, so when we plug this in, that means we are using a to be 0, where a is an ordinary point. Because we know this, for this case, singular points at plus or minus 2. So 0 is an ordinary point. Since we can define our y this way with a equal to 0, so this becomes same type of problem that we did in section 3.1. So all we need to do is we find all the derivatives. And then plug them back into the equation. Now, when we plug it back in, we want to plug it back into this equation because usually we try to avoid having to deal with fractions. So we plug it back into the original one. And then we're going to distribute the functions inside the summation. And now we're going to rewrite the second term so that it has x to the power n. So that means we're going to do n plus 2. And now, in order to keep the summation starts from the same term, originally it starts from C2, so here we have to change n to be 0. And then we copy down the rest. Oh, I think there's a right here. Right here, this is y prime, and y prime, I've already changed it to be starting from n equals 1, so I have to switch this to be n equals 1. So I have to change this to be starting from n equals 1. And same thing, change here to be n equals 1. There we go. Okay, now everything is in terms of x to the power n. Now we need to make sure they all starts from the same value in the sigma. So we can see the largest value is 2, so we need to rewrite all the rest so that they all starts from 2. So we're going to keep the first one. And we are going to write out the terms corresponding to n equals 0 and n equals 1. So I have to do minus then n equals 1. This is C3, 3 to x. And then the rest can be represented by sigma. Same thing here. We want to write out when n equals 1 and then the rest. Same thing here. When n equals 0, n equals 1, and then the rest. Okay, now we'll look at all the sigmas. They start from the same value. They have the same x power, so we can combine them together. And then we combine we combine constant term and x term together. These two will give us 4c1x. Oh, I think I'm missing, sorry, I'm missing constant here. This is, I was only looking at here, but the equation is so long. It starts from right here. So let me write the constant, and then plus C naught, that's a constant term. And then x power. So this is -4 times 3 times 2, C3, then plus 4C1x. And 4C1 comes from this 3C1x and C1x. Add them up. And then everything else. And that has to equal to 0. So then we set each coefficient equal to 0. And then we're going to set everything in the bracket equal to 0. Oh, I think I missed over here. I missed the first term from the summation. So let me add it back in. So then you can see all these three terms has Cn as a factor. So I'm going to factor it out. Okay, now we sought for the one with the largest index. And I'm going to calculate this. And then simplify. And this is what we call the recurrence relation. And this relation works for n greater than or equal to 2. Because we can see C3 is given by this form. So the next one we're going to need to have is C4. So that corresponds to n equals 2. So this is true for n greater than or equal to 2. Or you can think of this as it comes from this sigma notation where n starts from 2. Okay, now we're going to try to find a pattern. So we're going to plug in n equals 2 and look at what C4 is. And then we're going to use C2 equal to C0 over 8, plug it in. And then compute C5. And then plug C3 in terms of C1. For C3, let's rewrite C3 as this one should be a 2. I'll erase this. Should be a 2 C1. because C3 is C1 over 3 times 2, which is C1 over 6. So that's the same as 2C1 over 4 times 3. Yeah, to rewrite this way, the reason is then we can write it as 4 squared times 5 times 3. Or let me write the smaller number first. 4 squared times 3 times 5. All right, now C6. First use the recurrence relation and then replace C4. And C7. All right, so now we can see a pattern. That is, for the even index, we can think of it, everything, so here is even, this is even. So we can think of the top as starting from 1 times 3. That's for C4. And then C6 is 1 times 3 times 5. So we can think C2n as 1 times 3 times 5 times, but we always stop one less than the index, so it should be 2n minus 1. That's what we observed from the previous terms. 6, there's a 5, stop at 5. If it's 4, stop at 3. So here, if it's 2n, we stop at 2n minus 1. And then the denominator, we can see here when n, so think of this as 2n, where n equals 2. So this is 4 squared. Think of this as 2n, n equals 3, 4 cubed. So n should match. And then the denominator is 2 times 4 times 6 until we get to 2n. And they all depend on C0. And for the odd index, let's find a pattern. They all start from 2, and then they all end one number less than the value of the index. And then this is the denominator. And they all depend on C1. Okay, now notice two times 4 times 6 times up to 2n. Every number is a factor of 2. So if we multiply all those 2's together, totally we have n of them. So we have 2 to the power n. And then what's left is exactly n factorial. So we can represent 2 times 4 times 6 times up to 2n by 2 to the power n times n factorial. And then in terms of the notation for 1 times 5, 3 times 5 times 2n plus 1, we denote it by 2n plus 1 double factorial. So now we can represent C sub 2n by like this. And we can simplify it because 4 to the power n is 2 to the power 2n. And 2 and 2 have the same base, so we can add the exponent to be 3n. And then we can rewrite all the odd index. And again, simplify. Because in here, this is 2 to the 2n. Okay, now we can write down the solution. So the sum, the sigma, we can write out the terms, the first two terms, n equals 0 and n equals 1. That's our C naught times 1 plus C1 times x. And then for the rest of the terms, we're going to divide them into even index and odd index. And in fact, if we combine the first two terms, factor out the C naught, and do the same thing, factor out the C1, then there will be an x term here. Well, I don't know why I switched the index name to be k. It doesn't matter. You can call it any name you want. You can still keep it as n, just a name of the index, but then all the values are exactly the same. All right, now we're going to satisfy the initial conditions. So to satisfy the initial conditions, we're going to use the original form without knowing explicitly what are CNs. So we're going to use this. When x equals 0, y equals 4. So we have C naught plus the rest are O0. So C naught is 4. And then Y prime we are given when x equals 0, y prime is 1. So we know C1 must equal to 1. Therefore, our yx can be solved. And again, in here, what name you give doesn't matter. You can call it K, you can call it N, just make sure all those match. Okay, so that's it for today.